The final measure of dispersion that we are going to calculate is called the standard deviation. The definition of deviation is it's the distance a data point is from the mean. So it would be x minus x bar, where x is the data point and x bar is the mean. So if we come to this example down here, this data value, then we initially talked about if 9.5 is your mean, then the data value of 9 would be half a distance from the mean, but because it's to the left, it's going to be considered to be negative. So it's your data value minus your mean. So 9 minus 9.5 is negative 0.5. This data value right here has a deviation of 8 minus 9.5, or negative 1.5. This data value out here has a deviation of 5 minus 9.5, or negative 4.5. So then overall, these deviations summed together on this end would be negative 6.5. All the negative indicates is that these data values are going to be less than the mean. Over here on the upper end, this data value has a deviation of 10 minus 9.5, or positive 0.5. This data value has a deviation of 12 minus 9.5, or 2.5. And this data value has a deviation of 13 minus 9.5, or 3.5. If I were to add all these positive deviations, the positive deviations sum to positive 6.5. So there's where if we sum the deviations together, they sum to 0. Earlier when we were talking about the mean, all we were interested in was that we got the same number up here. But then if we start putting signs on them, if it's to the less than the mean, it's negative, and if it's greater than the mean, it's positive, then we can see the deviations would sum to 0. That's what it would imply for the mean to be the balancing point of the data. The standard deviation is the average of these deviations, and it's the measure of how much the data differ from the mean. Now, we can't just average these numbers up, right? So these would be all of my deviations. We're not just going to be able to add them up and divide by how many there are, because if we were to add up all these deviations, they would always add to 0. So the standard deviation does sum a couple of steps in the meantime to calculate what that average deviation is. Now the standard deviation calculation is kind of a long and involved calculation. It will involve several steps. In the real world, where we have really large data sets, the standard deviation is computed using statistical software or calculators. We are going to be doing the standard deviation by hand, and it's going to be expected that you will be showing your work about where the standard deviation calculation is coming from. Because the expectation is you're going to be doing the calculation by hand, your data sets will be fairly small, because it is kind of an involved process. Before getting into some of the details about standard deviation, the final thing I want to mention is, as a reminder, that you are allowed to use a note sheet on your exam. So on your note sheet, there's where you would put down the steps to compute the standard deviation. You wouldn't be expected to have this from memory, but if you have the steps on your note sheet, you then would be expected to know how to properly apply it. Now we would use the symbol S when we go to find the standard deviation of a sample, where you're going to use the symbol, and it looks like a O with a tail on it. This is a Greek symbol. It's pronounced sigma. For the standard deviation of a population. Now, the standard deviation is actually computed differently if you're finding the standard deviation of a sample versus the standard deviation of a population. So we are going to learn how to find the standard deviation of a sample. We won't be talking about how to compute the standard deviation of a population. Now, an interpretation of what the standard deviation is, the larger the standard deviation, the more dispersion there is in the data. In other words, the more spread out or variability the data has. So between these two examples, notice that they have the same mean, but these two data sets are going to have very different standard deviations. If you have more dispersion in the data, or the data is more spread out, you're going to have a larger standard deviation. If your data is more tightly clustered about the mean, then you're going to have a smaller standard deviation. Okay, so in these two data sets, just by eyeballing what's going on with the data, this data set down here is going to have a smaller standard deviation. So in this one, the data is more tightly clustered about the mean. So this is going to then be a number that gives us an idea about what's going on in the spread. So let's learn how to actually compute the standard deviation. So I've got these steps up here, and then ultimately this is the formula that kind of summarizes what's going on here. The first step is to find the mean x bar of the data set. As a reminder, how do you find the mean? You're going to add up all the data values, divide by how many there are. Once you have the mean, then we're going to go to step 2, where for each of the data values we're going to find its deviation. So the deviation is going to be computed by doing the data value minus the mean. Once we find all these deviations, the next step is to square all of them, and then we're going to sum them. So that's what's going on in this numerator right here. This says that you're going to find the mean, you're going to find the distance the data value is from the mean, you're going to square all of those numbers, and then this symbol right here, this is the capital version of that sigma letter. This is a summation notation. This just says take all those numbers and add them all up. So you're going to sum all those square deviations. Then for the next step, you're going to divide that sum by n minus 1, where n is the number of data values in the data set. And then finally, you're going to take the square root of the resulting number. Now, a couple of notes before we get started in this example is that in step 2, once you find all these deviations, if you were just to sum them right there, they would sum to 0. So that's maybe a good thing to check as you're doing this, just to make sure that you have found all of those differences correctly before you start squaring all of them and running through these last steps. Now also, when computing the standard deviation, we should not round until the very, very end. Most of the examples that we'll be giving you guys, just because you'll be doing them by hand, the numbers will always be integers or fairly simple values, so that way there's not too many intermediate decimals that you have to keep track of when you're doing this. Alright, so in this first example I have what happened in Abel's class and in Babel's class in terms of these test scores. So in Abel's class, the scores were 100, 80, 70, 50, 50, and 10. In Babel's class, the scores were 70, 70, 60, 60, 60, and 40. For both of these classes, let's go ahead and find their mean. So for the mean in this one, I would add up all these data values and then divide by how many there are. So if I were to add them all up, I would find that the mean is going to be then 360 divided by how many data values there are. So in this particular example, there are 1, 2, 3, 4, 5, 6 data values. So I would have 360 divided by 6, or 60. Now before going any further, let's go over to Babel's class. So in Babel's class, let's add up all those values to find its mean. When I add up all these numbers, I also get that they add up to 360, and then I would divide by how many data values there are. And in this data set, I also have 6 data values. So I would have 360 divided by 6, so I also get 60 over here. So these two data sets have the same mean, but something very different happened in the actual data. So while the mean is important, it is not the only thing that is going on inside this data set. So now let's take a look at the spread, and we'll determine the spread by calculating the standard deviation. For Abel's class, let's go ahead and find the deviation for every one of these scores. So for the first data value, its deviation is 100 minus my mean, which is 60, or 40. The second data value has a deviation of 80 minus 60, or 20. The third data value has a deviation of 70 minus 60, or 10. The fourth data value has a deviation of 50 minus 60, or negative 10. Then I would have 50 minus 60, which is also negative 10. And then finally 10 minus 60, which is negative 50. So at this point in time, notice if you were to sum all these deviations up, they would sum to 0. Each one of these deviations, we're now going to go to the next step and we're going to square them. So 40 squared is 1600, 20 squared is 400, 10 squared is 100, negative 10 squared is positive 100, negative 10 squared is positive 100, and then negative 50 squared is 2500. So now we're on to the next step where we're going to sum these square deviations. So if we were to sum all these numbers up, they would sum to 4,800. So now we're getting ready to run down these last steps. We're going to divide this sum by n minus 1, where n is the number of data values. So in this data set, my value for n would be 6. So the standard deviation, I'm going to take this sum, I'm going to divide it by 6 minus 1, which would end up being 4,800 divided by 5. And then ultimately we want to take the square root of this number. So I would want to take the square root of that. Now notice this entire fraction is underneath the square root symbol. So we're going to find what this number is, and then we're going to take the square root of it. Or you can throw this whole thing in your calculator all at once. So I'm going to pull up my calculator. So I'm going to find the square root of 4,800 divided by 5. Now all of this is underneath the square root symbol. Notice the parentheses here. So my calculator is going to do the division first, and then it's going to take the square root of whatever that number is. And it looks like out to 2 decimal places we're going to get 30.98. Alright, so there's the standard deviation for Abel's class. So now we're going to repeat this process for Babel's class. So for Babel's class, let's find all these deviations. So the data value minus the mean, so 70 minus 60 is 10, 70 minus 60 is 10, 60 minus 60 is 0, 0, 0, 40 minus 60 is negative 20. And again, notice all of these sum to 0 at this point. For each one of these deviations, let's square it. So 10 squared is 100, 100, 0 squared is 0, negative 20 squared is positive 400. Let's sum all these square deviations. So all of these would sum to 600. So then the standard deviation, which is denoted S, if we wanted to notate this, so the standard deviation S is going to be 600 divided by, now in this data set I also have 6 data values, so this is going to be 6 minus 1, or 5, and then I want to take the square root of whatever this is. Alright, so this is what I'm going to throw in my calculator. So the square root of 600 divided by 5. So the square root of 600 divided by 5. So out to 2 decimal places, it looks like it's going to be 10.95. So let's make that go away. This is approximately equal to 10.95. Notice in this first data set for Abel's class, there is a lot of dispersion in the data that resulted in a much higher standard deviation. In Babel's class, the data was more tightly clustered about the mean. The standard deviation of that data set was less.